During our literature review, we found that the primary accelerant is temperature. Thus, we can use the Arrhenius law and equation, which we have outlined here and we are quite familiar with during our course study. Again, the Arrhenius theory allows the test of any device under accelerated environments for short periods and then predicts the behavior under normal conditions for the longer periods. So what we're able to determine is basically the acceleration factor for elevated temperatures. This is quite nice in that our literature review has determined that the predominant accelerant to this failure mode is temperature, because this allows us to be able to implement or suggest, as we go through our analysis here, a burn-in period. For in real-world applications, if you have multiple stress factors, many times it's cost prohibitive and equipment prohibitive to embark on a burn-in per se that involves these two stresses and implement that in a costly manner. So in this particular case, temperature is the dominant acceleration factor, it may be worthwhile and cost efficient to implement a burn-in screen. We have found during our literature review the intrinsic data retention defects, the activation energy is equivalent to 0.6 eV. Thus, utilizing the Arrhenius equation and the activation energy of 0.6 eV, we have obtained a curve of the data retention versus temperature, which is displayed in this graph here. We can see from this graph that as temperature increases, the data retention number of years decreases. And this is a normal flow. So for this particular application, the use temp is 50 degrees C. So from the use temp of 50 degrees C, we would expect a normal data retention on a good NOR flash cell to be roughly around 20 years. And we can tell right off the bat from our initial data, without even doing much analysis, that this is not the case for this particular data set. Now we'll begin into our analysis summary. The first step of our analysis was to determine the distribution of each population. We attempted to do this by utilizing the chi-square goodness of fit test. Basically, what we have here are two different parameters that we're looking at, are two different hypotheses that we're investigating. The null hypothesis is that the data follows the specified distribution. The alternative hypothesis is that the data does not follow the specified distribution. The test statistic that we're using follows a chi-square distribution. So what we would do is we would determine the chi-squared test statistic from the particular distribution that we're investigating and compare that against a chi-squared given for a particular confidence level and degrees of freedom. We use this analysis for three specific cases. We use the chi-square goodness of fit test to look at the exponential distribution, the Weibull distribution, and the log normal distribution. Again, the reason why we chose the chi-square goodness of fit test is that it is very flexible in evaluating multiple distributions for appropriate use, as long as we're able to calculate the CDF of the part of the particular distribution that we're after. If we're able to calculate that and have estimates for the parameters of that distribution, then the chi-square goodness of fit test is applicable. So to further discuss the chi-square goodness of fit testing that we performed this analysis for both populations, the unscreened and the screened population. We then utilize the software Weibull++ to give us the distribution parameters, such as in the exponential case lambda, in Weibull C and M, in log normal T50, along with sigma. So therefore we use the Weibull++ software to get these distribution parameters for both cases, and then we implemented the chi-squared goodness of fit test by then predicting the expected number of failures for the given time periods under investigation, and then comparing them against the actual failures and then determining the test statistic. So what we have here is the summary of the results. We can see from this that this analysis was not straightforward. The data that we have does not fit nicely into any one of the particular distributions that we were using for investigation. We would reject basically the null hypotheses and choose the alternative hypotheses in all cases. We can see that in the exponential case for the unscreened population, that all test statistics are greater than the given baseline chi-square distribution at 90% confidence level. So we would reject every single one of these distributions. The same goes for the screened population. We can see that all test statistics are much higher than the baseline distribution at 90%. So again, all of the distributions that we studied during this course would be rejected. This is, again, I think to note that in real-world applications, not all failure distributions fit nicely into a textbook distribution. So we continued our analysis by using additional distribution determination techniques. By that, what I mean is we utilize Weibull++ and Weibull++'s distribution wizard to help us in determining the type of distribution that the data follows. Again, we use the maximum likelihood methods for determining and ranking the parameters and distributions. In the case of the unscreened population, we can see that the best fit for this population of failures is the G gamma, or the generalized gamma, followed by a three parameter Weibull, and then by a log normal distribution. Under the screened population, we conducted a similar analysis using Weibull++ wizard's distribution to help us determine the proper lifetime distribution to be used for this data set. And what we found, which is quite interesting, is that the software picked the log normal distribution as the best fit, then as number one, followed by log, and then a 2-parameter Weibull. And this is interesting because during our chi-squared goodness of fit test, we rejected basically the log normal along with the Weibull, 2-parameter Weibull distribution. One thing during our research also on the chi-squared goodness of fit test, one of the drawbacks in this particular technique, although it's very flexible for evaluating multiple distributions, but the drawback is that how you bin or how you make your intervals can affect the test statistics. So that may be a case here where our binning methodology was not appropriate and gave us results that led us to reject the log normal distribution, in which the Weibull++ software uses much more sophisticated population distribution determining methodologies and came up with the best fit of a log normal. So based off of this information, we would accept the log normal distribution for the screened population and the G gamma distribution for the unscreened population.